So, good afternoon, students. We'll be doing end-fire array today, and how the questions can come, which is related to design of the end-fire array. So, we have to see how the radiation pattern is formed. So, let's get in and see what's an end-fire array. So, end-fire array is something in which you'll see number of identical elements which are fed with currents of equal magnitude, but their phases vary progressively along the line. So you can see there are n number of elements that we have placed here, but like if one is 0 degree, the other will have a phase shift of 180 degree. They'll be equal in magnitude, they're equally spaced at a distance of d along the array axis. So the direction of maximum radiation, where is the maximum radiation, is always along the array axis. The maximum radiation will always be along the array axis in case of an end-fire array. So let's look at some of the characteristics of this, right? So what are the characteristics of end-fire array? So some of the characteristics are that in an end-fire array, so I'll just write it as end-fire array. Don't use the abbreviation during the exams. It is end-fire array. The direction of maximum radiation, the direction of maximum radiation coincides with the array axis, right? So if we are going to look for this, then if this is your 0 degree and this is your 180 degree, we are saying that the radiation pattern is going to look something like this, right? We will have minor lobes and all, but the maximum is in 0 and 180 degree direction. So again, we are considering a linear array system only. That means if you've done the array factor derivation, we are going to do something like that only. This will be first element, second element, third element, and we'll take a point P here, and we will join it to this point and join it to this point and, join it to the third point. So this is going to remain same, electric field of each is E naught. The total here is ET. Your psi will be 0 for this. So we're taking this distant point in the far field region. Now, what will be the alpha in the first case? This is the reference point source. So alpha will be 0, then alpha will be 180 degree. Then for the next element, it will again be 0. Then for the next element, it will be again 180 degrees. So it goes on for n elements like that. So for an end-fire array system, we're looking at the characteristics. So one is the radiation pattern. Where is the maximum radiation occurring in an end-fire array? Second thing that we must know is that for end-fire array system, your psi will be taken as 0. Alpha is not equal to 0, right? Because there is a phase difference between the adjacent elements this time, right? It's not like broadside. They are not same. So the phase difference, one is 0, then one is 180. So the phase difference between the adjacent sources is not the same. So what is the total phase difference? But total phase difference can be 0, right? That is the psi can be equal to 0. The psi is the total phase difference at the point P. And alpha is only between 1 and 2 or 2 and 3. So that's why that difference should be known. Now, what is psi? So is equal to beta d cos of theta plus alpha, right? So that means beta d cos of theta plus alpha will become 0 because I'm taking psi as 0 here. Okay, now I'm taking theta as 0. Now, what is this theta? Why I've taken it as 0? Because it is the maximum radiation in this direction. If you look at the end fire, the maximum radiation is in 0. So this is basically theta, which is 0. So I'm taking this as 0 plus alpha is equal to 0. So I can say alpha is equal to minus beta d. Right? Now, what is this alpha? I can further write it as minus beta is 2 pi by lambda And let's say I'm just assuming that this D, that is the separation between the elements, this D I'm taking as lambda by 2. It can be anything depending on our design. So I've assumed my D, I have assumed to be lambda by 2. Okay, so if I do that, then 2 gets cancelled. This is gone. What am I getting? Alpha as minus pi. So I'm getting my alpha as what? Minus pi. So this is one of the characteristics of the N-fire array system. Now let's look at the directions. Now we already know how the radiation pattern is, but we need to know in what direction this minor lobe is going to come. In what direction is this other lobe going to come? I need to know these directions, directions of the pattern maxima. Where is the maxima happening? Where is the minima happening? This, is called as a major lobe. So in which direction it is happening? It is very simple actually. Let's see the directions. So I'm writing it as the directions of pattern maxima for major lobes. Right? So this is your 0 degree, this is your 180 degree. And this is how you're going to get your radiation pattern. So the major lobe, so I'm going to take it as theta. Theta standing for the maximum radiation. So theta max is nothing but the maximum radiation of the major lobe. So it is going to be the maximum radiation of the major lobe is 0 degree or it is 180 degree. Right? So now let's talk about the minor lobes also. Major lobes are very simple. Now we have to talk about the minor lobes also. So the directions of pattern maxima for minor lobes. So the total electric field, E of t is equal to E naught sine of n psi by 2 upon sine of psi by 2. This comes from the derivation of array factor. So please do the array factor derivation first and then come for this particular derivation. So for maximum of minor lobes, ET is maximum. So now if sine term has to be maximum, that means sine of n psi upon 2 has to be equal to 1. Because the maximum value of sine is 1, right? So in this expression, that is ET is equal to E naught sine of this expression, your sine term has to be maximum. In other words, if I say E naught is 5, for example, then this has to be 1 because this has to be again 5. Then only it will become ET will become 1 maximum, or ET will be considered as maximum. So the sine n of psi by 2 has to be what it has to be. It has to be 1. So we're coming to that part. So let's see what to do. So that sine of n psi by 2 should be 1. So n psi by 2 is equal to sine inverse of 1. That means n psi by 2 is equal to, I can write it as plus or minus 2n plus 1 pi by 2, right? Where n is nothing but 1, 2, 3, etc. So this is pure calculation part, nothing much about it, but you should know these calculations. N psi by 2, because it's sometimes a 12 marks question, 15 marks question, because this is basically the design. So this is pi by 2. So psi can be written as plus or minus 2n plus 1 pi by 2 into 2 upon n. So what is psi equal to? Plus or minus 2n plus 1 of pi upon small n, right? Now I'm just putting everything back into what is the psi. Psi, if you remember, is beta d cos of theta plus alpha. So I'm going to put that back. So this will become beta d cos of theta max, of which lobe are we finding? For the minor lobe, plus alpha is equal to plus or minus 2n plus 1 pi upon n. Now for end fire, we had found something. We had found that alpha is minus beta d, right? We had found this. Now we are putting that in this expression. So beta d cos of theta max into minor minus beta d is equal to plus or minus 2n plus 1 of pi upon n. Now I'm doing some shifting here. Beta d is common, so that beta d will come down. I will get cos of theta max of minor, I'm writing min, minus 1 is equal to plus or minus 2n plus 1 pi upon in, I will get this beta d also, right? So what is the direction? That is, if I want to take cos of theta max in the minor, that means what is the direction of the maximum radiation of this minor lobe? In which direction? It can be written as I can write it as cos inverse of plus or minus 2n plus 1 pi upon n beta d plus 1, right? So I took that minus 1 on the other side, right? So we will get that this is the direction of the maximum radiation of the minor lobe. Now it is all about substitution. We will be taking different values because we are designing basically. So we're taking different values. So let's say if your small n is equal to 4. Now what is small n? N is the number of elements or the sources that we consider. So let's take it as 4. I have just taken random example. D is lambda by 2, the spacing. Alpha is minus pi. Beta is 2 pi by lambda. And capital N is 1. So N starts from 1, right? It decides how many minor lobes are there. So capital N is very important. It decides how many minor lobes are there. So what happens to our theta max? It becomes theta max of minor is equal to, what did we get? Cos inverse of, I'm just writing that formula, substituting the values in the formula. So what am I going to get? You can check this. It comes to 3 by 4 and plus 1. So we will take it as cos inverse of, we'll take two values, right? One will become 7 by 4, plus of this will take, and minus will give us 1 by 4, right? Now 7 by 4 we cannot consider. Why? Because cos inverse of 7 by 4 we will get more than 1. You can check it on your calculator. Cos inverse of 7 by 4 will become more than 1. And maximum value of cos is 1. So we will discard 7 by 4 and we will write only 1 by 4. So it is very simple. It is not difficult. But you'll have to revise this video at least 1 to 2 times, right? Then maybe when we meet on the third, you can ask me doubts regarding the same, right? So this will become theta max in the minor, or the first minor we are looking at, right? We are looking at the first minor. We take in the first one. This, if you put in the calculator, I think you get 75.5 degrees. So you can give it a check. Now, similarly, you should try for n equal to 2, because last May we have to draw the radiation pattern, you know. So similarly, the same formula, I want you to try for minor 2. I hope you're understanding. We have to draw the final diagram. So we need which angle where the minor is. So this will be cos inverse of, again, you substitute and you should get 5 by 4 and 1. You can check 5 by 4 plus 1. So this will become cos inverse of, you will get again two values, 9 by 4 and minus 1 by 4. Again, 9 by 4 is not possible. So cos inverse of 1 by 4, right? So this angle of theta max for the second minor that is minor 2. Where is it going to come at? It is coming at 104.5 degrees. So this is how we find out where is the minor, where is the, where is the major lobe and what angle it should be. Now this is the maximum direction, maximum where is a minor. There can be minimum value of minors also. So in the next part, I'm going to teach you how to find out the direction of minimum, because every lobe will have minimum and maximum. So this minimum for minor lobes. These minor lobes also, some places will be maximum, some places will be minimum. So what is that direction? So for minimum direction, we will be using the ET formula, which we have studied in case of array factor, that is n psi by 2 upon sine of psi by 2, and this factor must be equal to 0. In that case, the sine of n psi upon 2 should be equal to 0. So n psi by 2 is equal to sine inverse of 0. Everybody knows is plus or minus n of pi. Right? So this psi is equal to plus or minus n pi 2 upon n. Again, you know what is psi value. So I'm going to substitute psi. So what is my psi value? It is beta d cos of theta minimum, right? Theta minimum of the minor lobe. So I'm going to write minor here. Plus of alpha is equal to plus or minus 2 pi n upon small n. So for end fire, you know that alpha is nothing but what? Minus beta d, which is equal to minus pi. We have already seen this before. Substituting, it will become cos of theta minimum of the minor lobe minus 1 is equal to plus or minus 2 pi n upon small n. So I'm writing the theta minimum directly. You can take the minus on the other side, take the cos on the other side. So it will become plus or minus 2 pi n upon beta d n plus 1. So you will get this kind of expression for finding out the minimum direction, where the minor has the minimum direction. So again, we have to take different values of n and check. So I'm going to start with n is equal to 1. I hope you understood now how to do it. So theta minimum of minor is equal to cos inverse of what this is, plus or minus 2 pi into 1 upon this is beta, this is 2 pi by lambda into lambda by 2 into 4 plus 1, right? So if I solve this, I'm going to get 3 by 2, you can check and see, and half. Okay, so this is going to come something like cos inverse of, you will get plus or minus half plus 1. So please check the calculation. And again, 3 by 2 is not possible. So we will take cos inverse of half. And that means it is the direction of the minimum of the minor lobe is in plus or minus 60 degree. Similarly, we can take for if n is equal to 2. So if I take for n is equal to 2, theta minimum, again, you can try the calculation. It is very simple calculation. You will get cos inverse of plus 1 plus or minus 1 plus 1. So again, this is going to be cos inverse of, you will get 0, 2. 2 obviously I'm not going to consider. So I will take cos inverse of 0, and this gives me a direction of plus minus 90 degree. So what we are essentially doing is we want to draw the radiation pattern. So we are trying to get different points when n is 1, n is 2, n is 3. So let's do one more. If n is equal to 3 also I will consider. So if you take this, the direction minimum of the minor 3. So we have already seen for minor 2, we have seen for minor 1. So we are going to see for minor 3. And so this is going to be 5 by 2. You get minus half after substituting in the formula, which is going to give you plus or minus 120 degree. So we have a lot of data with us, with the help of which we are going to draw the radiation pattern. So let's see what we have till now. We have to draw the radiation pattern, and for that, what data we have in hand. So what data we have in hand? We have our direction of the maximum of the major lobe. This is going to come in 0 degree or 180 degree. Then we have the direction of the maximum of the minor lobe, which we are getting as plus or minus 75.5 degree or plus or minus 104.5 degree. Then theta minimum of the minor lobe, which we are getting in the direction of plus minus 60 degree, plus minus 90 degree, or plus minus 120 degree. So we are getting it in different directions, and now we are going to draw the radiation pattern. So you can think about how the radiation pattern is going to come now. So I'm drawing roughly, you should draw it very neatly. This is 180 degree, this is 0 degree. This is your 90 degree to 70 degree. Now think, our major lobes, we know where it is going to come already. See that they're symmetrical when you're drawing. I've considered 4 elements. So n is 1. 1 is a reference element, then 2, then 3, then 4, isn't it? The distance between them I have considered as lambda by 2. That small d I have considered as lambda by 2. So this is the basic distance d. Now you think about where the minor lobes were, right? So 1 we had got. So how is it going to come? How am I going to draw it? It's going to come like this and like this. Pardon my drawing. Wait 1 minute. Just a second. So I'm taking different values, the values that I have got, 75.5, 104.5, and 120 degrees. So don't forget what values you're getting. So 60 opposite to 120, minus 120 degree, minus 104.5 degree, minus of 75.5 degrees. So this way, you are getting the 4 element radiation pattern of the end-fire array. So this is what is expected from you. Now this part, that is this part to this part, is theta, is also theta. So we take this as 2 theta, which will become your first null bandwidth. So that is to be considered. So, we will, the beam width, basically. So let us see the beam width. So what is the beam width of the major lobe? So what is the beam width? We'll find out what is this. This is the beam width of the major lobe. So this is the beam width of the major lobe. So let's look quickly. In the last part, we will be studying about, or we have to include this in the design question of end-fire array, major lobes, right? So what is this beam width? This beam width is 2 into the angle between the first nulls, okay, and the maximum of the major lobes. So that is where I have shown you in the figure. So this will become 2 into theta 1. Now what is this theta 1? It is plus or minus under root of 2n lambda upon L. So now again, I'm doing it here only. If your n is equal to 1, then your theta 1 will become plus or minus under root 2 upon L by lambda. So therefore, your beam width of the first null between the major lobe, basically you're looking at the major lobe, will become 2 upon L by lambda. This is in radians, okay? Now, if I want the same thing in degrees, the conversion of radians to degree, 1 radian is around 57.3 degrees. So I have to multiply this. So I'm going to write VW Fn, the beam width is plus or minus, it will become 114.6 under root of 2 upon L by lambda in degrees. So how much is 1 radian? It is, so I'm basically multiplying this factor by 57.3 degrees. So this is the entire part of the end fire array design, which is one answer of 10 to 12 marks. Please do it. It's very, very important. Thank you.